signatures. All right.
Sorry.
No worries. Time scales and like how we can measure these temporal signatures of what galaxies do over time. So before I start, I do want to mention that this work has been made possible because of an incredible amount of support and insight from all of my collaborators. So I'd like to thank them and the collaborations that I'm a part of before I jump into the talk. To begin with, uh, I want to talk about why galaxies are interesting, right? So galaxies are collections of stars, gas, and dark matter, and they come in an incredible variety of different forms. So regardless of what kind of quantity you choose to talk about galaxies, for example, you can talk about what they are doing when you observe them. So some galaxies are actively forming stars, some galaxies are passive or quenched. They seem to have stopped star formation activity. Others seem to stop and then start again. These are called rejuvenated galaxies. And others stay passive for a very long time before bursting into a flurry of activity late in their lives. So there's this incredible diversity of what galaxies do when you observe them. There's also a lot of diversity in what they look like. There's galaxies that look like well-ordered disks. There's others that seem to lack any distinctive shape and just look like a spheroid or an elliptical galaxy. And there's all of these pictures that show galaxies that look like all kinds of weird interacting systems that defy any straightforward classification. There are some galaxies that even look like jellyfish, right? So there's this diversity in what galaxies do, what galaxies look like, and basically any other property that you choose to talk about a galaxy. So whether you talk about components of the interstellar medium of galaxies, things like dust and metal content, whether you talk about what's outside the galaxy, so the kind of environment that they live in, whether you talk about things that shouldn't even be affecting galaxies, like the central supermassive black hole and what it's doing, whether you talk about the assembly history, how this galaxy has built up its mass. In all of these quantities, there's this incredible diversity. And galaxy evolution is essentially trying to take this zoo of galaxies, so to say, and make order, make sense of how we get this, what kind of physical processes are responsible for creating and maintaining this diversity over cosmic time. So if you go into the literature, right, and if you look at what's happening, like what are the physical processes that are regulating galaxy evolution, that are responsible for kickstarting or seizing star formation over time, you see that there's a whole range of processes, things that happen on a galaxy wide scale to things that happen in small pockets, small clumps of dense cold gas where stars are actively forming. So there's this range of processes that happen over different spatial, but also over different temporal, different time scales that are responsible for figuring out whether a galaxy is going to be forming stars, whether it's going to continue forming stars, whether it's going to stop, for figuring out how it's going to look like, for figuring out how it's going to grow in size or change in morphology. And so you can see that like there's more than 4 orders of magnitude on this plot of timescales over which these different processes act, or at least are thought to act in the theory, right? So these are very broad ranges, but that doesn't mean that they occupy this entire range. It's just that current estimates think that the timescale lies somewhere in this range for most of these estimates. And figuring out the precise timescales and then correlating these to signatures that we see in galaxies themselves will allow us to then make connections between what's happening in galaxies and then which of these physical processes is responsible for that. There's also additional complicating factors, considering that there's a lot of overlap between these different timescales. So if you see a signature on a certain time scale, that means that it could be one or more processes that are responsible for what's happening then, right? Uh, so basically, figuring out galaxy evolution requires us to know two things. One, observational signatures of timescales on which something significant is happening. And second, a connection between that timescale and the underlying physical process that tells us that, okay, this process is responsible causally for the thing that's happening. And these connections are essentially what I'm going to be talking about for the rest of this talk. The talk's going to cover a decent bit of stuff, but I'm going to be talking in part about observations and how we can get at timescales, and then about simulations and how we can interpret these timescales. So it's key to understand that different timescales tell us about different parts of galaxy evolution. On the largest timescales, you know about things like mergers and galactic winds and feedback from central supermassive black holes. It tells you things that are responsible for starting up and turning off star formation galaxy wide. On intermediate timescales, it tells you about things like feedback and wind that essentially causes baryon cycling, which is responsible for cycling gas around and across galaxies. And then on the shortest timescales, it tells you about the burstiness, about the stochasticity of star formation, and talks about what kind of mechanisms could be responsible for that. And the way timescales help us, like here's a specific example. And I'm going to, for this example, use this excellent figure that Alison Mann and Ciro Belli came up with that talks about galaxy quenching. And so galaxy quenching is something that we can observe. It's something that people are now able to, with some amount of robustness, measure quenching timescales for. But it could be because of many different causes, any of which can occur at different stages of what a galaxy is doing, and which hopefully have different characteristic timescales on which they occur. So if we can get a quenching timescale, and if we know characteristic timescales for all of these processes, then the hope is that we can correlate quenching timescales with which process is responsible for quenching at a given mass, at a given redshift. Right? So we can figure out what the dominant physical process at a certain epoch for a certain population of galaxies is. And that can help us explain this diversity of galaxies that we're observing. So the way we measure timescales, right, is through these things called the star formation histories of galaxies. So star formation history is a curve that tells you about the star formation rate of the galaxy as a function of time. So these are three curves from the Illustris TNG simulation. And they just show for three of the galaxies in that simulation what the star formation histories look like across time. So one of them rises early and then quenches quite rapidly and remains quenched for the rest of time. Another one is slightly later, and another one is still ongoing star formation at the present time. So here is where we would observe it if we observe it at redshift 0 at 13.7 billion years. So when we talk about timescales, we can talk about about many different things, right? So we can either fit these star formation histories with exponentials and then measure like a decay timescale. This is something that's commonly done. You can use something like a peak finding algorithm to talk about the full width half max. So essentially the lifetime of a galaxy. Or you can fit something like a Gaussian to it and say that this is the average mode of how long this galaxy has been forming stars. But all of these don't manage to capture the full uh, detail in terms of the complexity of the star formation histories we're looking at. So the rest of this talk is essentially going to be dedicated towards how we can measure star formation history information from observations, and then how we can take star formation histories from simulations and try to interpret them, quantify their variability, and talk about physical processes that are linked to this variability. So before I jump into that, are there any questions so far? All right. If not, let's jump into observations. So observations come in a variety of shapes and sizes, but the one that I'm going to be talking about today is something called the spectral energy distributions, or SEDs, of galaxies. And these are essentially multi-wavelength observations that have been at this point done across a whole range of wavelengths, ranging from the submillimeter to the X-rays, that are then used to predict physical properties like the star formation rates, the stellar masses, the ages, metallicities, and so on of galaxies. And the goal here is to then use these physical properties or collections of these physical properties for large samples of galaxies to identify how physical processes like feedback or baryon cycling are responsible for galaxy growth. So there's two challenges that I've outlined here. One is that these observations are noisy. They often have limited wavelength coverage or resolution, and that different physical processes can cause similar signatures in the observations. So you have parameter degeneracies, and that, like, because of that, you end up seeing the simultaneous effect of multiple things happening. So how do we disentangle that, right? So there's a well-known degeneracy between age, dust, and metallicity. And so one ray of hope in the current situation is that our observations are getting better with time. And so with every year that passes, we have observations that have higher signal to noise, higher resolution. We also just have an increase in statistics overall, and an increase in sophisticated techniques that help us analyze this data. So there is hope for disentangling these effects. Specifically, let's talk about how star formation histories are dealt with. So I showed you some complex looking star formation histories earlier, right? Things that had jagged shapes and had a lot of variability. But for the longest time, we weren't able to get that information, right? And to a certain extent, we still aren't. So what people often do is make simplifying assumptions. A lot of SED fitting analysis that care more about derived quantities like stellar masses and star formation rates deal with the star formation history often as a nuisance parameter that just needs to be marginalized over. So what they do is to take simple parametric forms like exponentially declining or constant or linear rise followed by exponential decline. Take forms like this that have a few parameters that need to be fit, and say that the best fit in this case is a rough idea of what the star formation history, underlying star formation history, looks like, and then we'll just go with that. So this works uh, better than you'd expect, but it still causes biases in the estimates of things like stellar mass or star formation rates, and it certainly doesn't give you an idea of what the actual star formation history looks like. So in recent times, as the signal to noise, as other things have been improving, uh, there have been non-parametric ways of measuring star formation histories that people have used. So uh, I'm showing three examples of this. The first one is to divide time into bins and then measure the star formation rate in each bin as a free parameter. The second is a really interesting way where you take a cosmological simulation as a prior of what actual galaxies might look like, and then take star formation histories from these simulations, and then just calculate the likelihood of each of these star formation histories given your data, and then use a Bayesian technique to create a median. And the third one is something that I spent some time developing back in 2017. It's essentially where you take multiple parametric forms and you combine them to create these effectively non-parametric shapes when you have enough signal to noise. So all of these have their advantages and disadvantages, but none of them is truly able to capture all the variability that you might see in a star formation history and scale that as a function of signal to noise. So this is something that I've spent some time developing and come up with something called the dense spaces method, which is an approach to star formation history reconstruction that has three cornerstones. One is that it must be physically motivated. The second is that it should try to encode as much information as possible in as small a number of parameters as we can. And this sort of information compression is intriguing because it provides you with a basis to talk about star formation histories in. And then the third is that there should be a correspondence between how well we do in the space of observations and how well we do in the space of the reconstructed star formation histories that we want to do, that we want to use in our analysis. So we want to make sure that all the uncertainties in our observations get propagated into uncertainties in the star formation histories that we reconstruct. So with that, the first version of this was to just consider multiple parametric forms and then combine them when the statistics allow it. So stack as many parametric forms on top of each other as we can, given that the signal to noise is good enough to do so, right? But this still had like the sort of underlying parametric scheme to it, and it's difficult to scale up to uh, computationally do this when you run into a large number of parameters. So I spent some time and we came up with this description for star formation histories that solved a lot of this. So we now have flexible star formation histories that do not depend on any underlying functional form. And the way we do this is by describing a star formation history using this tuple that I'll elaborate further, along with something called Gaussian processes. Now, before I go further, are there any questions at this point? All right. So
yes,
I'm going
I
to...
have a question.
Okay, go for it.
Yeah. Because you were mentioning constraints on trying to fit these the constraints for these models, or this physical understanding of star formation, what affects the star formation. Could another constraint, which you haven't mentioned, and maybe that's something that will be used in the future, the morphology of the star formation regions within each galaxy. Can you use that as well eventually?
Yeah, absolutely. I mean, when I was developing these techniques, it was to fit the photometry of distant high redshift galaxies. So we didn't really have much morphological information. We just had the integrated photometry for each galaxy. But as I look at more and more nearby or resolved galaxies, the morphology within galaxies is definitely an additional source of information that I want to mine. So yeah, that's a great question. Thank you. All right, so before I get into the star formation history part of this, I want to give a blazing fast introduction to Gaussian processes because they are the coolest thing. So Gaussian processes are composed of two things, right? A Gaussian, which is this distribution that we all know and love, that has closed form solutions in a lot of operations that we do. So when we do integrals, when we calculate gradients, when we try to write likelihoods that are a Gaussian or a sum of Gaussians or a product of Gaussians, they all have closed form solutions. So it's useful in a lot of cases, combined with something called a process, which in this specific context is a collection of random variables that's indexed by something like time or space. Like basically it has a coordinate. So what this means is you can think of a process as a sort of random walk, except at any given time t, it has a well-defined distribution. And as you can probably guess, for a Gaussian process, this distribution is a Gaussian, right? So at any given time t, it's a random walk where the distribution is Gaussian. And what this allows us to do is to take the simple Gaussian, which is a PDF, a probability distribution that is defined at a single point, and extend it to the space of functions. So now you can talk about sort of Gaussians in the space of functions and then try to constrain them with data. So a Gaussian process is essentially something that's shown in the top right corner. So this is a prior distribution, and the lines themselves are samples from this prior. So when you have no information, then it just has a mean of 0 and a variance of 1. And when you sample from this, you see that these samples sort of all will average out to have a mean of 0 and the variance that you set. In addition to this, you also give it one extra piece of information in the form of a covariance function. So that essentially tells you that if you have the Gaussian at time equals 2 and the Gaussian at time equals 10, it tells you how these Gaussians are related or correlated. And once we have observational data, so every point we add to this is a constraint that takes this Gaussian process and narrows down the space of possibilities by saying that it has to 1 sigma of the time pass through the observational constraints given at that point, right? With the uncertainties that you provided. So Gaussian processes can be thought of as another kind of spline, right? It's a way to perform interpolation or essentially get a smooth curve. But unlike a spline, this is something you can also put covariance information into. So if you have some physical intuition about what the covariance between 2 points should be, then that's something you can put into this. It's also something that naturally accounts for uncertainties because you're doing all your computations with a Gaussian. So this approach is Bayesian from the get-go, right? So if you have observations with uncertainties, it will create a Gaussian process, which essentially tells you the mean and uncertainty at every point, even the points where you don't have data, right? So when we're talking about star formation histories, especially non-parametric star formation histories, where we have few constraints, you can start to see where this would be extremely useful. So the way we talk about star formation histories using Gaussian processes is using this tuple, where we give the constraints as the stellar mass, which sets the overall normalization, the star formation rate, which sets the normalization at the time of observation, and a set of parameters Tx, which are the look back times at which the galaxy forms certain fractions of its mass. So T25 would be the look back time at which it formed 25% of its mass. T50 would be when it formed 50%. T75 is when it formed 75%, and so on, right? So these are integral constraints, which mean that when we do the Gaussian process, we don't do them in star formation rate versus time. We do them in the integral of star formation rate versus time, and we draw a Gaussian process there and differentiate that to get the star formation history. So when we take these three constraints, right, these three Tx parameters, and so these three Tx parameters correspond to this blue curve. We don't pass in the blue curve. We just use the blue curve to calculate these three parameters as an example, and then tell the Gaussian process, okay, create for me a curve that satisfies the same constraints. And it creates this, right? So even with just three parameters describing this curve, it's able to create a very good approximation of the entire behavior, the rise and fall and subsequent rise, again with the slight dip at the end, that the star formation history has. And that's kind of incredible because it's not using much information at all. If you don't have even the three parameters, if you just have one parameter that you can define from, that you can get from your data, then this is how the Gaussian process does with just one parameter. So it still gets a rough idea of the shape, but not as well. It doesn't get the rise and fall, for example. If you give it two, it starts doing a bit better. The two parameters in this case would be T33 and T66. And with three parameters, you already saw that it's starting to do quite well. And if you give it 5 or even maybe 11, it starts approximating the true curve better and better. So as the number of parameters goes to infinity, it will exactly approximate this true curve. But that's not something that we are ever going to get with observations. So we usually deal with n param ranging between somewhere between 3 to 8 or 9. So Gaussian processes in this dense basis description allow us to talk about star formation histories, about like a wide range of different star formation history shapes with even just a single Tx parameter. So when we have more parameters, we now get like usable constraints on the shape of the star formation history that we can use for further analysis. So, and this is just how the things look when we actually do analysis in the space of observations. So on the top is a plot showing the SED of a galaxy, which is these blue points along with their uncertainties. And then the black spectrum and the points essentially show the fit to the spectrum. And then on the bottom panel, you see the true star formation history, because this particular SED comes from a simulation, along with the reconstructed star formation history and uncertainties around it. So uh, we bake in a technique using model selection. So we essentially use something called the Bayesian information criterion to determine, while we're fitting the SED, the optimal number of star formation history parameters that we can extract from it. And this allows us to make sure that if there is information in the observations, we will get it out. And that this method becomes future proof, in the sense that as our observations get better, we'll be able to get more information out of the observations as well. So to summarize, the dense basis method gives you a flexible parameterization that allows you to describe star formation histories using uh, this mass star formation rate TX description, and use Gaussian processes to create smooth star formation histories that satisfy these, and all the while keeping the number of TX parameters flexible so that it's future proof. And this method itself has its own code. So there's something called the dense basis code that's available in public and is now being used by a handful of groups. But there's also, like, it's an implementation, right? It's an algorithm. So there are also other SED fitting codes like bagpipes that now offer the dense basis style of star formation histories in fitting. So if this is something that's of interest to you, please let me know and we can talk. And what this allows you to do, right? Like, once you have these star formation histories, you can run this code on a large number of galaxies and then look at how star formation histories evolve across cosmic time. So what this plot shows is the star formation histories of about 50,000 galaxies in the Candles survey, ordered such that you're going in increasing stellar mass from left to right and decreasing redshift from bottom to top. So the universe is getting older as you go from bottom to top. So this is essentially showing you on the bottom left corner the youngest, highest redshift galaxies in our sample and how rapidly they are forming stars. And as you go from the bottom left to the top right, it's showing you how quenching is starting to set in. And specifically, it's starting to show you signatures of the timescales on which these galaxies begin to flatten out and turn over and stop forming stars, as a function of what mass they are at, as a function of what redshift they're at. So this is a plot that I have stared a lot at, and the more I stare at it, the more it seems to tell. But summary statistics are usually useful. So let's talk briefly about all the different things that we can do with star formation histories like this, right? Feel free to bug me about these afterwards, but because I'm going to be rather brief about each specific topic. So the first thing is you can measure things like stellar mass and star formation rate much better than the simple non-parametric forms that people have been using in the literature. So in terms of both the bias and scatter, you get better results when you use the dense basis method. And what this leads to is that when you look at scaling relations like the stellar mass star formation rate correlation, there's been this tension between observations and simulations for a while. And when you use the dense basis estimates, the tension gets resolved, because now we are able to estimate these quantities more robustly. You can find galaxies that actually show evidence for multiple episodes of star formation. So galaxies like this one, where there's a rise, a fall, and then a rise again. And you can look at that fraction as a function of stellar mass and try to get constraints on feedback or on processes that can cause this kind of quenching and rejuvenation. And you can also look at the amount of time this whole endeavor, like the time between two peaks, takes as a function of stellar mass and redshift. And this remarkable thing that we find is essentially that this fraction as a function of this quantity expressed as a fraction of the age of the universe is remarkably constant across redshift and across stellar mass. So we are now looking at simulations to try to interpret what this might mean. You can probe inaccessible parts of scaling relations. So I briefly mentioned the SFR M star correlation. So this is correlation between stellar mass and star formation rate. And as we go to high redshifts and low masses, galaxies get fainter observationally, and it's harder to see them, or they're more noisy. So what we can do is, using star formation histories, we can say that like a single galaxy is not just a point on this SFR M star correlation, but it's actually a trajectory. It's this whole, it's a pathway along which a galaxy evolved over time. And so we can take a galaxy and translate it back in time, either to higher redshift or back in time to when it was lower in stellar mass, and see what it was doing back at that earlier epoch. And so this allows us to essentially like add a third dimension of time, to take observations that are high signal to noise at low redshifts, so bright objects, and translate them backwards along time to see what they were doing at higher redshifts. And this can be used as a remarkable predictor for upcoming surveys, like what's going to happen with the James Webb Space Telescope. And we can make predictions to see whether we actually observe those. And even if we don't, then that's physics that's new that we can then study. We can link features to galaxy morphology. So this is not submorphology, but overall, if we just take morphological classifications. So if we divide galaxies that are disks, or just disk plus bulge, but dominated by the disk component or the bulge component, or that are pure spheroids, you can have, and you look at their median star formation history, you can see that there's a coherent signal of sorts, where it seems to go from star forming to quenched as you go from a more disky to a more elliptical profile, right? And so there's a lot to be studied in terms of quantifying the link between star formation history and morphology. And it's not just morphology, you can also talk about environment. So you can do the same analysis where you take galaxies that have a different amount of neighbor galaxies nearby, and so you can quantify this over density factor and bin galaxies by the over density that you find them in. And you also now find a trend between star formation history shape and the kind of environment that they live in. So there's all of these really interesting things that you do, even with this high redshift sample. And as we go to lower redshift, as we have better, more spatially resolved observations, we can, for example, with the SDSS manga survey, we can actually go in, use the dense basis method to quantify spatially resolved star formation history information, and look at things like quenching timescales and how they vary spatially as a function of where in the galaxy you're looking. So this is all new and exciting. And if this excites you too, please talk to me about it. I'm happy to elaborate further. I also have,
Kartheik,
yeah.
just on the on that. So are you just using the manga IFU data, or you have other sort of constraints on the SED?
So currently this is just from the manga IFU, the like the data cubes. But I'm talking with collaborators in about using result photometry as well to get wider wavelength coverage. Yeah.
So I was just wondering if you have any sort of quantification of how well you do with just the manga data. So just the narrow wavelength coverage.
So it really depends. Like, we do quite well when it comes to stellar masses and star formation rates. In terms of star formation histories itself, we are figuring out, like, there's discrepancies between the reported like pipe 3D, which is this other spectral code that was used to fit the manga data. We are figuring out that there's some discrepancy between their star formation history estimates and ours, and like why that is the case. But overall, we're able to constrain things to, like, so this map, for example, shows you the T50, which is the look back time at which it formed half of its mass. And so this is a quite well constrained parameter. So It depends on like what kind of uncertainty you're looking for. But I think even the current manga data allows you to get quite good constraints on star formation history.
Interesting. Okay, thank you.
I mean, I'm happy to talk further about this if you'd like.
Yeah, I mean, I'm just curious, basically, as to I didn't realize you could basically just take that narrow wavelength coverage IFU data
So
and get
there's a lot of absorption and emission lines that let you like the main part of the wave of the spectrum that lets you quantify star formation histories is rest optical.
okay.
And because the manga data essentially samples that in brilliant resolution, we're able to get quite a lot of information.
Cool. Thank you.
And so I just want to mention a student of mine, Caleb Lammers, who's working on essentially scaling up this process using neural network architecture uh, to essentially learn what the dense spaces code is doing and then do it, but much faster. So I think he submitted a poster for the Casca meeting, so you can see more of it there. And with that, I'm going to briefly head into simulation land and talk about cosmological simulations and their star formation histories and what we can hope to learn from them. Before I do that, are there any questions on what I've said so far?
Yeah, I have a question about, you had a 3D plot there. It was, let's say, time.
Yeah.
We had a couple of them anyway. Star formation and the stellar mass and star formation rate. And it had yeah, that one. That's the one. What I'm fascinated by is are all the threads in there. It looks like there are threads in there that have maybe be bunching in certain ways. I'm just wondering, does that bunching tell you something? Can you do some kind of analysis and quantify that bunching and learn something about star formation from that?
Yeah, absolutely. That's a fantastic question. So I'm glad you brought it up. So what the colored points are here are galaxies that are observed at different redshifts. So the universe was of different ages. And so the green points are galaxies at redshift 1, the purple ones are galaxies at redshift 2, and so on. And then the threads for each point are the star formation histories. So it's showing you the evolution as a function of time in this stellar mass star formation rate space. So if you take a slice of these threads at any point, it essentially tells you the scatter in the stellar mass star formation rate as probed by these like trajectories, right? And when you compare that with like the actual scatter that's observed at that redshift, you're essentially seeing the difference between intrinsic and observational scatter.
Right. But
So,
I was wondering about how the threads, I mean, if you put the threads together and you have some kind of way of characterizing the way they bunch to each other, is there something, I mean, there's just something you can do there that would be interesting.
right. So there's been this question for a long time about whether or not this SFRM star correlation is an attractor or whether it's so a lot of people call it the star forming main sequence, which is not a term that I fully agree with, but it essentially says that like galaxies spend their time in and around this correlation with minor wiggles up and down, as opposed to other theories that say that no, galaxies essentially travel along their own trajectories. They just happen to group together in this correlation because of gas physics. So looking at how the threads bunch together could potentially allow you to answer this question of whether or not this correlation is an attractor. Yeah, I mean, that's something I still want to think about because there's complicating factors that come into this.
Right.
But yeah, that's the hope.
Right, thanks.
Yeah. All right. So now let's jump into simulations. So simulations are incredible. They are, so the current generation cosmological simulations have come a long way since pure collisionless n-body codes. And they simulate the full suite of physical processes ranging from magnetic fields to baryonic physics to gravity to electrodynamics. And they have this huge dynamic range, high resolution. So there's a lot of good stuff in there that we can learn about galaxy evolution by looking at the outputs of these simulations. But there's also certain limiting factors. Uh, a lot of the processes that happen in galaxies happen on scales that are so tiny compared to the size of the galaxy itself that even these high resolution simulations aren't able to fully resolve them, and often have to introduce something called subgrid recipes. So these are recipes below that tell you analytically what happens below the resolution of the simulation. And that can potentially introduce artifacts into how the galaxies end up finally looking like. Um, Another thing is that different physical recipes for what we think happens in galaxies can correspond to different timescales. And so these physical uh, implementations of things like black hole feedback in different simulations can give rise to different timescales on which we see signatures. So there's this question of how realistic any one given simulation is, right? Like, what's the best representation of our universe? So when we talk about these things and we want to look at star formation histories of the galaxies that arise naturally in these large simulations, we wanted to introduce something that can quantify the amount of variability as a function of time. So we introduced something, well, we didn't introduce, but we used something that exists in the literature called the power spectral density. So this is essentially the power in a time series uh, as a function of time scale. So if you take a sine wave and you do the Fourier transform, you break it down into long, medium, and short wavelength contributions. For this sine wave, there's just a single time scale. So you in the PSD see a single peak. If you instead consider a combination of multiple sine waves, then you can then Fourier decompose it into long time scale, medium time scale, and short time scale components. And so now the PSD has multiple peaks that correspond to each of these things. And finally, if you consider something like a stochastic series, so this is analogous to the process part of the Gaussian process that we talked about earlier. That too decomposes into long, medium, and short time scale components. And these processes usually have characteristic features in the PSD, like a slope or a slope followed by a cutoff or something. So things like Brownian motion, white noise, these all have characteristic PSDs. So what we then did is we started taking star formation histories and Fourier transforming them to find their PSDs. And we did this by for a large number of different simulations that we collected data from. So here's an example of how this works. The gray curve is the full star formation history. The blue curve is the sum of the Fourier components up to a certain time scale shown on the right. And then the black is just the mode that comes from that particular time scale. And so essentially like the black can be thought of as a band pass across different time scales or across different frequencies. And they all sum up to give the star formation history. So what this allows us to do is to then talk about this power spectral density or PSD, which quantifies how much burstiness there is in star formation histories at a given time scale. And the first thing we see when we do this for different large box simulations is that the PSDs and the star formation histories of these galaxies look quite different across the different simulations. And even in cases like Illustris TNG versus Eagle, where the star formation histories themselves look similar, there are still notable differences in the PSD that tell you about the different physics that gets put into the simulation. So instead of just trying to look at this by eye, we decided to quantify this difference by looking at the strength of the PSD on the x-axis and the slope of the PSD on the y-axis. And we, for just one simulation, show here like how things look like at different timescales as a function of increasing stellar mass for this particular simulation. And if you look at this, then this might give you an idea that says, oh, okay, I understand what the slope versus the strength of the fluctuations look like at a given mass. and now I can build a model and look for this in my observations. But when you do the same analysis for other simulations, so right, these are at 3 different time scales. So these are essentially cuts at these 3 different time scales, showing you what the PhDs are doing. And so if we do this for just one simulation, it looks like we have a model for what galaxy evolution is predicted by these simulations look like. But if we redo this analysis across a bunch of simulations, you see that they're all over the place, right? There's really no common trend between these PhDs for what they do as a function of stellar mass or what they do at a particular time scale. And this is remarkable because this means that we have this new space where observational constraints are going to come in and dramatically change what we know about star formation histories by saying that some physical processes work and some don't, right? So there's this really wide ranging and reasonably sensitive space where we are now looking for observational constraints to come in and tell us which ones of these trends are closer to our universe. So constraints on this will give you a lot of insight into the mechanics of the way we implement feedback or baryon cycling in these simulations. There's also dark matter accretion history PhDs that we can look at. And these show a lot of self-similar structure, which is consistent with what we know about dark matter halos, in that their accretion behavior is self-similar over time. And what you can now do is do a cross correlation between the in situ star formation history. So not the mergers, but just the stars that were formed in the galaxy itself, and the dark matter history PhDs, and see that they are coupled on long time scales, but not at short time scales, right? So that also makes sense because on shorter time scales, there's all of these baryonic and feedback processes that regulate how galaxies form stars. On long time scales, galaxy evolution is tied to how their parent halos evolve. And
about 4 minutes left, or just
all right, perfect. I have my last point to make. So this is good. So the last point I wanted to make is that we can also look at quenching through the lens of PhDs. So I've been talking about quenching observationally by measuring timescales, but we can go into the simulations, split galaxies according to whether they're quenched or whether they're star forming, compute their PhDs, and then take the difference at a given stellar mass. And that gives you the excess power in the star formation histories of the galaxies that are quenched, right? And because, again, these times are related to physical processes, we can look at where the excess power lies and then correlate that with the mechanism that's responsible. So this is also something we did for all the different simulations. And again, the simulations show a wide diversity in where the excess power in quenching comes from. In some simulations where quenching is put in by hand, like in Mufasa, where galaxies quench because the halo remains heated, so stars can form. You see that there's almost no low time scale power versions of the same underlying simulation and look at runs that have no AGN or no feedback due to different things like X-rays or jet mode feedback from black holes. And so this is explicitly correlating physical processes to observational timescales. And so we can put all of this together and maybe someday even look at zoom simulations, which have a small number of galaxies, but incredibly high resolution to see what happens on the shortest timescales. So on timescales that go from 10 million years to a few 100 million years, which is not accessible with the large volume simulations. So to summarize, characterizing timescales is important because it allows us to tie observational signatures to physical processes that regulate star formation in galaxies. Cosmological simulations allow us to study populations of galaxies and quantify their variability. And this tells us, it points us towards which timescales we should study. And then using tools like the dense spaces method and a whole bunch of other non-parametric star formation history methods that have come up in recent times, we can reconstruct smooth non-parametric star formation histories from their SEDs and get constraints on what's happening at these timescales. So with that, I will conclude. And I'm sorry for going over time, but I will be happy to take questions.
Thank you. That was great.
Thank you.
So I'm going to ask a quick question first, since I get to do that. Just a coding question for you. So there were a couple of comments in the chat that your figures are beautiful, right? Like your talk was just very aesthetically pleasing. Do you have, is it all just Matplotlib? Do you have like a color scheme that you use? Do you do it by eye? Like, I'm just curious.
Yeah. So yes, all my figures are pure Matplotlib. Regarding color schemes, I actually have a package on my GitHub that allows me to take frames from movies or any other image and generate a color scheme using a machine learning technique called t-SNE. So it essentially takes the frame, decomposes it into colors, and then you can pick 6 colors or 8 colors, whichever you want from it.
That's fantastic. Okay, cool. I will look at your GitHub later. I see William has a question.
Yeah, and your power spectral densities, you create those by taking the autocorrelation function first and Fourier transforming that. So I was thinking the autocorrelation function, I don't think you actually showed them specifically, or you might have shown a form of them, but did you actually look at the autocorrelation functions? Because those might be interesting in themselves.
Right. So, I mean, in doing the analysis that we did, we didn't actually compute the autocorrelation function first. We directly just took the star formation histories and used Welch's method to compute the PSDs. But yeah, they are related, like especially for the class of like damped random walks that we're considering as analytical models for the PSD. The Wiener-Khinchin theorem relates the autocorrelation function and the power spectral density. And I can show you plots for how this looks like because we are now implementing them within our Gaussian process. So let me see if I can share my screen. Yeah. So this is the class of autocorrelation functions that we're looking at. Like this shows you the correlations as a function of delta t.
Mm-hmm. And that's in gigayears, delta t?
Yeah, that's in gigayears.
Right.
So there's essentially like 3 timescales in here. There's a timescale for inflow, a timescale for equilibrium, and a GMC lifetime. So this is essentially coming out of this analytical model that Sandro Takela, Neven Kaplar, and John Forbes published last year. So I can link to that paper if that would be useful.
Thanks.
Cool. So one last question from Marta.
Mm-hmm.
Yeah. Hi. Thank you, Samantha. So thank you, Kartheik, for your talk. It was super interesting. I have a couple of questions on the simulation side. So you said that you were interested in cosmozooms because they can go to smaller resolutions.
Yeah.
What resolutions would you need to explore those tiny timescales?
So the main thing we can't do with the cosmological volume simulations is look at GMC lifetimes and the contribution from feedback that happens on that time scale, supernova feedback, cosmic rays and things. So things like FIRE or Alison Brooks's like DC Justice League simulations allow us to go to 1 to 20 million year timescales, which is what we need to probe those, to probe that physics.
Okay, yeah, and then that links to my second question, which is, have you considered simulations that actually resolve the multi-phase nature of ISM and not what Illustrious or Eagle does, which is just put everything in some sort of warm gas, because that's going to influence a lot your star formation histories.
Absolutely, yeah, it does. So we have considered like 2 sets. So one is the FIRE 2 simulations. and one is back at Rutgers, Alison Brooks and the Gasoline Changa group have like the G14 Justice League Marvel simulation suite. And so both of these allow us to get close to the 1 millennia resolution, and for not for a large number of galaxies, so we can't do the stacked analysis that we've been doing otherwise, but you can still look at individual galaxies and see what they're up to. But no, it would be great if we had more. I mean, I'm always looking for simulations that allow us to get to these shortest timescales.
Okay, I might get in touch with you because I'm working on a suite of simulations that sounds like something it could be interesting to look at.
That would be great. Thank you. Yeah.
Yeah, of course.
Cool. And with that, we're at the hour, so I'm going to go ahead and end. Next month's talk is by Nina Gusinskaya at University of Toronto. Thanks for coming, everyone. If you want to be entered in the draw for a free Casca registration, please type your email in the chat window so I have that. Thank you so much, Kartheik. That was great. I'll leave this room open for a few minutes if anybody wants to stay and ask questions after, if you have time.
Yeah, I don't have a meeting now. So
okay, cool. Thanks, everybody.
Thanks for having me.